Good evening, everybody. Can people hear me at the back? Is it fine? All right. So, my name is Nishith. I'm a data scientist at Wargaming. And today I'm here to talk about some of the cool stuff we have been doing in machine learning around analyzing gamers' behavior in World of Tanks. Now, before I move forward, I just want to get like a brief idea. How many of you guys are familiar with Wargaming, World of Tanks, or how many of you are gamers? All right. All right, so we have quite a few people who are familiar, so that's good. For those who don't know, well, Wargaming is one of the leading gaming developers in the world right now. Some of the market leaders in the gaming scene, Wargaming has produced them. Wargaming specialization is particularly around military-based battles. So some of the flagship games we have are World of Tanks, World of Warships, World of Warplanes. We have them on multiple platforms. They are on Xbox, PC, mobile. There's all sorts of versions. So, definitely worth checking out if you're a gamer. So now, one of the things about Wargaming, and in general, like anytime you have some of these new gaming companies we have, they have been putting out these games. So if you notice, there's been this boom in applications development, in online gaming, the free-to-play gaming market. There's so many games coming out, so many people developing all sorts of applications. And if you look at the market leaders, they tend to have user bases that range to sizes of hundreds of millions of users. So you end up with these very interesting data science problems where you want to run sophisticated analysis, but you want to do it efficiently because you have such huge data sets. Before I jump into any specifics about the problem, I just want to spend a little bit of time giving you a little info around data science in Wargaming. So, Wargaming, well, we have recently opened an office in the Czech Republic. We have two offices in two locations. We have one in Prague, one in Brno. There's a lot of stuff we do at these locations. There's QA, data warehousing, distributed development, back office support, procurement and legal services in Prague, and then we have a lot of prototyping and development work in Brno. Wargaming I've worked in a lot of places, and Wargaming is a really nice place to work at. There's a lot of, we have offices all over the globe, so we collab, anytime there's a project, there's a good chance we end up, collaborating with people from different locations. I personally, like whenever I'm working on something, I'm collaborating with data scientists from Minsk or the United States. So it's a really fun environment. You get to meet people from different places, different backgrounds. You get to exchange all these really cool ideas with everyone. It really gives you a wonderful environment for growing yourself as an individual as well as a professional. So as I mentioned earlier, we have a global presence. We have offices all over the world. Some of the key locations which have BI presence. We have Austin, which handles strategic intelligence. I'm going to explain the meaning of all these blocks, but briefly, strategic intelligence is about understanding the market. What kind of games does the market want? Is it looking for a free-to-play, I want something quick and then I'm done, or is it a more hardcore audience? Things like, so the job of strategic intelligence would be to figure out, what do Xbox players in North America want to play right now? So that would be something falling under strategic intelligence. They would help plan out future ideas for development in games. We have support analytics. Support analytics, as the name implies, they do analytics for supporting the different departments in Wargaming. Any kind of financial forecasting, any kind of modeling required to, you could get a requirement that, hey, I want revenue forecast for the next 3 months for the North American server, or I want to know what's the trend in the, on the Russian server for how people are reacting to a new patch or a new update. So this is where, say, support analytics would come in. Then we have the user research division. User research is largely dedicated to surveying players. So these are people which actually go out, survey players. They do the A/B tests. They manually type out the questions, and then they design sampling techniques to select players, and then give them all these questionnaires to fill out. So our user research team is located in Minsk, and then we have publishing analytics in APAC, Singapore. Publishing is related to player relationship management and customer relationship management related tasks. So things like churn projections, helping design campaigns, models for predicting campaign responses. These kinds of problems come under research analytics. And then finally we have, publishing analytics. And then finally we have data science. Data science is sort of you could say data science is like a support layer for all of these analytics layers. So anytime, there's some heavy duty analysis that needs to be done, where that's when data science gets called into the picture. That, hey, we want to do this complex forecasting or this complex modeling task. Can you guys come in and help us? So this is just a brief overview of how BI or data science in general contribute towards a product's life cycle. So generally, you have an idea for a future game. You have strategic intelligence. They have feedback into, how to refine this idea. What does the audience want? What kind of features should the game have? You have telemetry design at that point, which is designing what variables to collect. For example, we know that if we want to understand the churn behavior of a user, we need to collect login data. We need to know when the user logs in, at what timestamp, when he logs out. So deciding what pieces of data to collect, how to collect them, that comes under telemetry design. So once we decide on the telemetry, that's when data services kick in. Data services, as the name implies, is the part of Wargaming that's responsible for designing the ETLs, the data warehousing and database capabilities to deal with all the data that's going to be generated by players playing the game. And then, of course, we have these various stages in the game's life cycle. You have the alpha, where alpha is sort of a point where your game is now ready to be tested internally. So we invite people from within the organization to start playing the game and give feedback. So at this point, user research can come in. They can start surveying people that what did you like, what did you not like, how do you want to change the game, so on. And then eventually you have beta, then you have launch. At launch, we want to start worrying about things like customer relationship management, player relationship management. So that's when publishing analytics, support analytics also come in at that point. And then, the game moves on into its eventual life cycle where it's launched. You're going to have patches, you're going to have special events, maybe special sales, special campaigns. So at all of these different key points, analytics has a very strong role to play. And as I mentioned earlier, data science is something that serves as a support group for all of these different pieces. So you can broadly summarize the focus of data science as it's really all about developing new methods, algorithms that support all of these different analytic functionalities. Generally, it's data science is generally called in when you want to build something more complex, where you want to build in some machine learning models, you want to build some state-of-the-art machine learning methods that can scale to large data sets, some sophisticated statistical models, and so on. And of course, once you start working on these interesting complex problems on these very large data sets, there's always a lot of opportunities to explore any new techniques, new methods, all sorts of new ideas and tools can be developed. So to be very specific, these are some of the things people at data science work on in Wargaming. So strategic intelligence, there's input on telemetry, what data to collect, life cycle analysis. By life cycle analysis, we mean life cycle of the game, like how long would we expect a particular game to last, how long will it saturate, etc. User research, estimating things like quantifying player satisfaction, user profiling, surveys, designing surveys. And then finally, we have game support, which is cheat bot detection, just trying to improve the general experience of the player. And publishing support, which is all about customer relationship management. And finally, we also use cutting edge technology. As I mentioned, we have a huge data set. Wargaming has many games that have been out for years, and there's millions of people playing these games every year. So over the last decade or so, we now have data sets for hundreds of millions of users that run, range of terabytes, petabytes. So any kind of processing would require some state-of-the-art technologies. So a lot of stuff we do relies on SAS. We use R, H2O. We are now transitioning into using NVIDIA for GPU-based processing. So these are all new cutting-edge things, especially if you want to start using things like deep networks. So all of this is cool, but what is before? So that was a general overview of data science BI. But I think you guys are more interested in a more specific problem. So let's transition into something more interesting. So the particular setting we have over here is what we call a non-contractual setting. So this is something that's really come about once online retailers, e-commerce has become really popular. In this particular setting, your user is not really obligated for any subscription services, any contracts, anything, right? You download an app, you start using it. That's the point when you commit to using it. And anytime you want to stop using it, you just stop using it. You don't really have to call or cancel or do any of that stuff. So this is a typical non-contractual setting. The big challenge over here is that your user churn is latent, right? It's hidden. You don't know when your user leaves the game. All you know is it's been a long time since he last logged in. So you use that information to make a guess. Okay, because it's been, 200 days he's not logged in, maybe there's like a 85% chance he's never going to come back. So you're going to have to work with uncertain probabilistic statements at that point. So a lot of ideas that we use for analyzing players in non-contractual settings. We start out with ideas from the marketing domain. And we do that because, frankly, the marketing domain has been studying this for quite some time now. So some of the original models, they came way back in 1987, where people were interested in physical stores. And the nice thing about these models is they work with very minimal data. They work with something called Rfm Measures. So is anyone familiar with Rfm Measures over here in the marketing domain? Okay. So I'll expand on this. So RFM stands for recency, frequency, and monetary. So these are three different dimensions, and you want to measure these three dimensions for each customer. So recency is when was the last time the customer showed up. Frequency is how often does he show up. And monetary, which is basically a measure of intensity. Every time he shows up, how much does he spend? How much time does he spend? How much money does he spend? That's the classic marketing scene. If we translate these metrics to our gaming scenario, then we have some very analogous measures over here. So recency can be when was the last time the user logged in and played the game. Frequency can be how often does the user play the game. And intensity or monetary can be every time user A has a gameplay session, how many games on average does he play. Three very basic measures that are easy to compute. You can easily compute these on very large data sets. You can, it's very easy to process minimal information. The only issue over here, of course, a lot of people would say is that, why not involve covariates? Why not involve things like age, gender, etc., the classic regression style method. We can do that stuff. The problem is that a lot of these mobile games, they don't want to collect that information. And a lot of game developers really don't want to get into that. There are many reasons for that. Privacy being one. Users don't want to report private information. Users misreport private information. I don't think I've ever reported a correct age on the internet ever. I'm sure many people don't either. So there's a lot of misreporting that happens. So the general idea is can we do something with objective data? By objective data means data that I can observe. So if I see the user logging in on Wednesday afternoon and then logging off 2 hours later, that's an objective measurement, right? There's no fudging or misreporting over there. It's a physical observation. So working with that kind of data, you don't have any of these issues around misreporting or noise and stuff. There's also another larger reason for that. We want to avoid collecting that data because there's a lot of churn that happens in your registration process, right? As a game developer, if someone is interested in playing your game, you don't want to bog them down with, give me your fill out this registration form, give me your age, give me your address. You know, people are going to leave if you keep bothering them, if you put this huge information form in front of them. So a lot of times it's even beneficial for the game developer that, you know, the user just creates a username and they start playing the game right away. So you don't want to bog them down with providing personal information. So that's another motivation why we want to have a minimal feature set that's just based on RFM. So now that we have established we want to use RFM, let's look at some methods from the marketing domain that work with these features. So the family of models I want to focus on today is called the buy till you die family of models. And the reason why it's called buy till you die is because it's a survival model. How many of you guys are familiar with survival models? Anyone? Okay. So what you do in a survival model is you use survival models when you're trying to model the time to an event happening. So these models, they find their origin, they find a lot of use in the medicine domain. Typically, they're used for things like modeling mortality rates of diseases, that kind of stuff. But they also find a lot of application in other scenarios. So over here, if we try to model when is the next time the user is going to log in, so that's a time to the next login. So you can treat it like a survival model that, okay, when is the next time to log in for this user, next time to log in for this user. And we use the word recurrent here because the user can log in multiple times, right? He can log in today, he can also log in 2 days later, and then after that he can again log in, maybe 1 hour later, maybe 10 days later. So he can keep logging in over and over and over. So it's a recurrent process. It keeps happening again and again. And the reason why we have this die part over here is because at any point in this process where the user is logging in, we also allow the user to churn out from this entire process. So at any point, the user can decide, I'm done. I don't want to be a part of this process any longer. So he churns out or becomes inactive. So this would be this is a nice pictorial representation. So here we have example of a user. We are following him on a regular timeline. We see that at time t1, we see this user for the first time. And then we notice that he comes in a total of 9 times. So we observe him first at t1, and then another 8 times after t1. And then let's suppose the user never logs in. After this last red tick, we never see the user. Because let's suppose the user has churned out at time tc, right? So how would we model this kind of a process? This is typically what happens, right, in a non-contractual setting. You have users logging in or visiting the store or buying something, any event that you want to model. And as long as the user is an active customer, he's going to engage in these events. But once the user decides, I'm done, I don't want to be using this service anymore, I don't want to play this game anymore, I don't want to go to this store anymore, then the user churns out and he's no more, he's not going to come back. So you want to have this probability of allowing the user to churn out, because if you keep modeling that user, that, oh, is just a guy who's going to maybe come back after 500 days, or maybe this is a guy who survives till time equal to infinity, that just throws off your model. It doesn't really work well. So this is a neat addition. Like I said, it's fairly straightforward. Your statistical model has 2 components. You have one component which controls for how long the user is active. The classical implementation of the buy till you die model, it uses a mixture of infinite exponential distributions. So you have an exponential distribution which controls your dropout rate. So you have mu I, which basically controls how likely it is for the user to drop out. The way the model introduces heterogeneity in this dropout rate, because everybody is not going to drop out at the same rate, right? If I have 100,000 customers, they are all going to behave differently. Some people like the game. They're going to have a very low chance of dropouts. There's going to be a segment of the population that's really not into, maybe they're not into, military style games. So those guys are going to churn out very quickly. They'll have a much higher dropout rate. So one of the requirements in such a process is to have some heterogeneity in your dropout rates for your customers. So which is why we have this gamma prior on the dropout rate. So you have an exponential distribution which controls the dropout or the churn behavior for each user. And then you have a gamma distribution which controls the dropout parameter, which controls the dropout for each user. And then you kind of have the same thing for how many sessions the user is going to have. Over there you use a Poisson process. And the Poisson has a rate parameter, lambda. And same thing, you let the lambda have a gamma prior distribution. So if I had data on people logging in again over time, and then they may come back, they may not come back, I could give it to a buy till you die model, and then I could estimate my gamma parameters, the R, alpha, S, beta, the shape and scale parameters of my gamma distribution. And that should give me a pretty decent summary of what's going on with my user population. I also want to mention that this is a classic case of the buy till you die model. You can have many different variations. It's actually an entire family of models. How you change, people have tried different things on how to model the dropout rate and how to model the playing rate. And different variations in how you model them give you different variations of the buy till you die model. For example, over here we have an infinite mixture of exponentials with a gamma prior. So that's a Pareto distribution. But another variation is where you have, this is basically you can have a beta prior or a Bernoulli parameter. So that's another one where it's like a coin toss. After every time you log in, you toss a coin to decide whether you want to churn out or not. So that's another variation. So you have different variations of these models. If you are interested, I'm not going to go into too much detail, but feel free to connect with me after the talk, or there's some references here. You can definitely look into detail. There's a lot of history around these models. They have been tested quite a bit on different data sets in the marketing domain. One of the things that has been shown in the marketing literature is that these models are really good at summarizing the average user behavior. So let's take a simple, I'm going to go over an example when I say what does it mean by summarizing and predicting the average user behavior. But this is generally a property of any homogeneous parametric statistical model, right? You have a homogeneous statistical model which assumes the same parameter for every user, right? Users are sharing parameters. So over here, we introduce heterogeneity by having a prior on mu I and lambda I, but ultimately the gamma prior parameters, the SB and the R alpha, they are shared by everybody, right? Everybody's dropout rate comes from gamma S beta, and everybody's playing rate comes from gamma R alpha. So this is, even though we have heterogeneity in the individual rates, it's still a homogeneous model. It's just a homogeneous model that allows infinite mixtures. So let's look at how does buy till you die do, how well it does if we do use it on some real life data set. So we're going to use buy till you die on data from the EU region. So we looked at World of Tanks players who joined between 1st Feb 2016 and 1st May 2016. So we took this roughly February, March, April, 3-month slice. We looked at everybody who joined in, and then we tracked these people for the next 1 year till 1st May 2017. And we looked at every day, and we looked at how many of those guys came back on each of the days between their date of joining and 1st May 2017, and we also looked at how many games they played every time they logged in. So we had a total of about 331,000, a little over 331,000 users, and between them they played a little under 207 million games. So you can see just a small 2-month slice gives you such a huge amount of games. And I should also mention that when I said that we have big data science challenges, this is actually true, because we have 206 million games over here, and Wargaming records very fine data. Like, we have data all the way down to which tank fired a shell at which point, whom did it hit, how much did it cause, damage did it cause. So you can imagine how quickly this data can grow very, very big. So we even have individual shells, information on individual shells fired on each of these 206 plus million games. So it's a huge data set. But for the buy till you die model, we are not going to go into all those details. We are going to work with simple stuff like win-loss. Not even win-loss, actually. We're just going to look at did he log in and how many games he played. So in order to see how well buy till you die does, we are going to set up a simple prediction problem. We are going to look at data for everybody from 1st Feb 2016 to 31st Jan 2017. And then we are going to predict how many games they are going to play in the next 90 days. It's a very simple prediction problem. And one of the things you can see that's going to make this prediction problem pretty difficult is the distribution of the number of games played. You can see that as we move across the quantile, the number of games played by people shoots up. In fact, if you look at the last 5%, it's going from 4 all the way to a little under 10. And this is on a logarithmic scale. So that's 6 orders of magnitude increase in the last 5%. That's huge. This is something, this is a phenomena that we observe a lot. This is not something intrinsic to wargaming or online behavior. This is a principle that was figured out a long time ago by Pareto. It's called the Pareto Principle. In marketing domain, it's also called the 80-20 rule, where, I don't know, have you guys heard of this? The Pareto Principle? So it's a very famous thing in business where this guy Pareto, he did a lot of research on distribution of income, distribution of wealth, distribution of revenue, and he figured out something that's consistent across all these data sets. He figured out that roughly a small fraction of the people, 10 to 20%, are responsible for 80% of the wealth. So that's where the whole, top-heavy stuff comes from. So we have the same thing over here. About 5 to 10% of our people are responsible for a huge chunk of the games. And then we have this huge set, the remaining 90% of the people that are responsible for a much smaller fraction. And we're going to see that in a little bit. And we've already talked about this. We are going to use RFM-based metrics. So this is one of our inputs. Now, let's look at global level predictions first, population level predictions. If you recall, we talked about how the buy till you die model does a pretty good job of capturing population level trends. And it does a pretty decent job over here too. We looked at the total number of games that were predicted to be played in the 90-day period. And the buy till you die model predicted roughly a little under 29 million games. And the actual number was a little above 31 million. So fairly close. But the nice thing is, if you look at the distribution, so on the x-axis, you have the actual number of games played. And on the y-axis, you have the log of the number of users who had that many number of games played. So you can see that there are lots of people who churned out. They had 0 games played. They churned out. They didn't show up in the last 3 months. Then you had fewer people playing 1 game, 2, 3, 4, and then your curve goes down. So this is something you see all the time. You're looking at distributions related to economic behavior. In general, like whenever you're looking at human activity, there's a good chance you'll come across this distribution. When you're looking at spending, you're looking at logins, you'll keep seeing this shape where you're going to have this huge chunk of the population that's going to have low participation, and then this small piece that's going to have very high participation. So it's like the 80-20 rule, right? You have a big chunk of the population that's playing fewer games, and then you have this tail over here where you have relatively much smaller number of people that make up the population of players playing large amount of games. Get it? And one of the really hard problems is, if you look at this distribution, it's actually really flat, very flat. And when you're trying to model it, what this means, it's very hard for the model to tell the difference between someone who's played, say, 1,000 games and someone who's played, say, 1,500 games, because again, if you recall the shape of an exponential style distribution, once you get to the tail region, the probabilities are very close, right? The probability of playing 100 games is going to be pretty close to the probability of playing 150 games. Just that's the nature of the curve. Your y-axis has a very tiny shift, while your x-axis can keep going forward. So one of the things we want to do, and we always do when we are working with data sets of this form, we try to exclude out the whales. We want to remove this annoying set of people. Well, I wouldn't call them annoying for analysis, but we want to remove this set of people that's throwing off our analysis, because, and it's really simple why we want to do that. Let's say your process has a naturally high variance, and it's extremely difficult to distinguish between someone who plays 1,000 games, someone who plays 1,500 games. And because these values are so large, the mistakes you make on these points, they end up dominating the behavior of your learning algorithm. So let's say I have someone who plays 5 games, and I predict this guy to play 10 games. It's a mistake of 5 games. So, which is fine. And I have clear patterns, right? There's a difference between someone who plays 5 games, someone who plays 15 games, because the distribution has a much better behavior. But if I'm trying to predict someone who's expected to play 1,000 games, I can predict him to play 1,000 games, but that guy could come back and play 2,000, he could play 2,500, he could play 200. It's really hard to pinpoint the exact number. And the mistakes you end up making on these points, let's say you predict 1,500 games. The guy comes and plays 2,000 games. That's a mistake of 500 games. And if you're using a squared error loss, that 500 becomes 500 square. And it's going to dominate the behavior of your learning algorithm. It's going to force your learning algorithm to fix this huge mistake first while ignoring everything else. So you want to remove these points. And once you remove the top 10% of the players, notice that the games go down to 33% of their value. So after removing the top 10%, we have a little over 300,000 people left. And the number of games, they go down from a little under 209 million to a little under 69 million. So that's like 10% of the people responsible for 66% of the games. A very top-heavy distribution. So now, all of this is cool, and buy till you die model does a decent, in spite of all these issues, we see the buy till you die model does a good job of capturing our population trends. So we're happy with this. This seems pretty reasonable, you know. I could give this to a CRM, customer relationship manager. He'd be like, okay, I could use this information to plan things, you know, plan future campaigns or any other stuff around this info. Now, but then the next question is, okay, it's doing well on the population level. Now, how well is it doing on the individual level? Now, before we look at individual level performance, I want to briefly touch upon some evaluation metrics I'm going to use. So we do well on the population level. How are we doing on the individual level? If you want to know how are we doing on the individual level, we need some way to measure the goodness of our result on individual level data. And you know, people who are familiar with statistics and machine learning, I'm sure they'll find these 3 errors quite familiar. Is anybody familiar with these 3 errors? I'm sure, or quite some of you are. Okay. So I can briefly touch upon error metrics. So anytime you have a learning algorithm, like let's take a classic regression setting, right? You have covariates, you have responses. Okay, sorry. Chalk, okay. All right, I'll just briefly put this. So you have a bunch of covariates and you're trying to model it, you have a response variable y. Typically, you have some subscript denoting the instance, right? This is a very simple setting. A lot of people are familiar with this. You're given this, you're given the x's, you're given the y's, and you want to learn some coefficients. That will satisfy this equality. So it's like a function learning problem. You want to learn what coefficients are going to combine your covariates in such a manner that you get your response variable y. And you do this because next time, if somebody gives me a bunch of covariates, I can go back to my W weights and I can then give him the value of y that he can expect to see for those covariates. So it's like a prediction, basic linear regression based prediction. So let's take a simple situation. Let's say someone asks me, okay, Nishith, I'm giving you this point, I don't know, x alpha. Tell me what value of y am I going to get? So I say, okay, I have my W coefficients. You're going to get some y hat. I estimate the value you're going to get for this point, x alpha is y hat. Let's call it y hat alpha. And then he says, oh, okay, you told me y hat alpha, but the actual value is y alpha. So now the next question is, how do we measure how correct is this prediction? So that's where these error rates come in. We want to measure the quality of our prediction. So the most popular one we use is something called the root mean squared error. It basically, all it does is it looks at the difference and it squares it. This is I think this is the most popular loss function around. And there's a very good reason why. It has a lot of very good properties. I won't go too much into what those properties are in detail because that will be going into deep machine learning theory. But the idea is that it's got nice differential properties. You can differentiate it everywhere, right? You can get it's easy to get the gradient, the Hessian. It's just really good for optimizing. It just behaves very well with optimization algorithms, with learning functions. Because the way any learning function works is you try to guess what these weights are going to be. And then you see how good your predictions are. And then when you say, okay, my predictions are off by this much, so I need to adjust my weights. Maybe I need to increase these two weights to get my responses closer to the actual response. So that's typically how any learning algorithm works. You have some measure which looks at the quality of your predictions, and then your learning algorithm adjusts whatever parameters or it's trying to learn such that this loss is minimized. Now, if we only cared about minimizing the loss on the data set we have, it's an optimization problem. It's not really a machine learning problem. The difference in a machine learning problem is not only do we want to optimize on the data we have, we also want to optimize on data that we could potentially see in the future. So that introduces a lot of elements related to things like denoisification. You want to figure out general trends in the data, but you also don't want to learn very specific trends because that specific trend could be something very specific to your data sample. So you want to play this balancing act. That's essentially what a learning algorithm is doing. It's doing this balancing act where you're trying to learn as much as you can from the sample you have, but you also want to generalize it to other samples from your data generating distribution. So you don't want to learn too much. That's called overfitting. We want to avoid overfitting. So just like everything else, too much is too bad, too little is also too bad. You don't want to underfit, you don't want to overfit, you want to get it just right. So Let's see. I'm going to briefly describe each of these error functions. For our study, I just want to have some few comments on the nature of these functions and what kind of influence they will have on the learning algorithm. So squared error. If you look at squared error, I mentioned earlier that squared error has this thing where it focuses on fixing the big errors, and that's because of the nature. Let's say yi minus yi hat is 10. That becomes 100 when you square it. If yi minus y hat is 1, it stays 1 if you square it. If it's 0.5, it becomes 0.25. So a squared error tries to fix the bigger mistakes. So if you have a situation where, oh, I'm doing really well on some points and I'm doing very poorly on other points, a squared loss function is going to try to bring this down. Because these are big errors, we don't want big errors. A squared loss function will give you something like this, something in the middle. It'll try to cut down these big errors. But it's going to happen at the cost of overestimating this stuff over here. So all these balancing acts. Another error is mean absolute error. Mean absolute error, again, fairly straightforward. It just looks at how much you are deviating from the actual prediction. And because you only care about the value of the difference, you don't care whether it's under predicting or over predicting. You care in certain situations, but when you're evaluating, you only care about is it the same or is it different. So you just measure how far away it is from the actual value. And then you have something called the mean relative absolute error. It's actually pretty much the same as something also called MAPE, mean absolute percentage error, if you guys are familiar with that. The only difference, the one thing to note is that this is a relative difference. So this over here makes a pretty big difference because now you're measuring your error relative to your response variable. So the difference over here is, let's say I have the actual number of games played as, say, 1,000, and my model predicts 500. This will give me a mistake of 500 square. This is going to give me a mistake of 500. This is going to give me an error of half, because 500 on a response variable that has a value of 1,000, that's just half. I'm only making 50% error. But if the actual number of games played by the person is 2, and I predict 5, this is 3 square, this is 3, this becomes 100% or 1. So so in a way this is biased towards the lower value responses. So, and this is something that we understand, that we have now understood in machine learning. The nature of your loss function is pretty much what defines how your learning algorithm is going to behave. And all these fancy techniques around regularization and all sorts of things, these are all just proxies of modifying your loss function to force your learning algorithm to behave in a certain way. In fact, that's also something we are going to be doing in this study later. All right, now that we have some evaluation metrics figured out, let's focus on the individual predictions. So these are individual predictions using the buy till you die model. On the x-axis, we have the actual number of games played. And on the y-axis, we have the predicted number of games played. Now, the way you should look at this graph is, if, let's say over here, you have a value of 10, that means everybody over here actually played 10 games. But you can see most of these points, they were predicted roughly in this region. So that's anywhere from 0 to, I don't know, maybe 400 something. And then it goes all the way up. So the red line is the actual, so the pink line is the average of all the predictions for this particular value on the x-axis. So this pink line point for the value 10, this will be the average of all the predictions for the response 10. Get it? So, and the red line is the ground truth. So the closer we are to the true predictions, the closer the pink line should be to the red line. But if you look at this picture, you can see that some of the mistakes the buy till you die model makes are really huge. Like, look at these cases, right? We are looking at it at the lower 90% quantile of players. So the number of games actually played go from 0 to 110, but the predictions go all the way up to, the mistakes go as large as 2,000. And the reason why this happens, you know, I could sit here and theorize all day, but one of the main reasons is that, again, your loss functions behave very differently. So the buy till you die model, we saw it had this, you know, this elegant model of having a Pareto distribution for the dropout rate, having a negative binomial, which is basically a Poisson gamma mixture for the arrivals, the recurrent arrivals. It has a loss function that works with that, which uses that information. The key takeaway is that because the buy till you die uses all these distributions, it associates a positive probability with someone playing these large number of games. So it has a tendency to give predictions which have very large number of games. It's not doing anything wrong. There are people who have very large number of games in the data set. So ideally, it's not doing anything wrong. There are going to be people who will have very large number of games in the data set. But from a learning problem perspective, it's not a nice thing to do, because we know there are very few people, even though there are going to be such people, there are going to be very few. So even though there are going to be some people who will have maybe, say, thousands of games, we don't want our learning algorithm to predict thousands of games, because if it does, it's going to make these huge mistakes. This is a very core thing in machine learning. This is another fundamental concept in machine learning. It's called the bias variance trade-off. So our process here has very high variance, right? We have people playing 500 games, 1,000 games, 2,000 games. There are people who go as up to, like, I've seen people, there are data points where people have up to 13,000 games. So it goes up by a lot. So what do we do in this situation? There's so much variance in my data, and if I use this, I can't predict with this data. So what you do over here, you actually bias your model. You do something called biasing. So you bias your model. What you do is you tell your model, you know what? Don't predict big values. Just don't do that. Don't choose any solution that's going to give me big values. So what are you doing here? You're basically, if you say there was some way you could force your model, hey, don't give me any predictions more than 500. Let's say you could do that. Now suddenly all these errors are, right? You're not going to be making any of these errors anymore. These 1,000 game, 2,000 game errors, they'll be gone. This is something called, this is basically forcing your model towards a solution that is a little inconsistent with the actual phenomena. Getting it? So this is basically something called biasing. An unbiased estimate would be something like the buy till you die model that tries to capture the phenomena with the variance and everything. But in these high variance situations, it's not working. We want a model that's going to trade off some of this variance error for bias error. So if we were to bias our learning model to give us lower predictions, yes, we are going to make mistakes on these guys who have very large number of games. But then on this huge population of 90% people, we'll actually end up doing better because those people don't play a large number of games. So we would actually want a model that associates zero probability with a large number of games, or very low probabilities, certainly much lower than the buy till you die model. So how do we do that? Well, let's turn to some very sophisticated stuff. Why don't we throw the latest and greatest stuff at the problem? So we are going to go to machine learning now, and we are going to use some of the one of the most advanced techniques of machine learning. So is anyone familiar with the concept of gradient boosting over here? Okay. So gradient boosting is it's a machine learning technique. It used to be the state of the art before deep networks became popular. It still is a very popular technique because it's like I said, it's an ensemble method. Ensemble methods are basically methods that use multiple models instead of a single model. Right? To put it in a very informal manner, think many minds are better than a single mind. So you use a bunch of weak learners and you combine them synergistically to have a model that's far better than each one of these individual ones. The core idea behind gradient boosting is actually pretty straightforward. You train a model on data, you train another model that learns where the first model is making mistakes, then you train another model that learns where. So once you learn this model, you can now predict using this model, and then you can make a correction using this model, so you have a better prediction. Then you train another model that learns the mistakes on this better prediction, so you have an even better prediction. And you can keep on iterating over this process. So what eventually happens is, if this is the error for a single model, for 2 models, this error will go down over here. For 3, it's going to go down further. Eventually, your error is going to flatline, or it's eventually you're going to hit a point. Oh, sorry. Eventually, you're going to hit a point where your error is, there's no more appreciable improvement in your error. So that's sort of, it's like the point of convergence. So you start out with one model, then you train the second one, which fixes the mistakes of the first one. So your error goes down. Then you train a third one, which brings it further down. Fourth one will bring it even further down. Maybe a fifth one will bring it here. And then, maybe there's no point in going further because you're not getting much reduction in error anymore. So that's really how something like gradient boosting would work. If you're interested in more rigorous explanations, you can feel free to get in touch with me. There are some references over here. It's a really cool technique, actually. The mathematics is also really cool. It actually learns the direction of the gradient, which reduces the loss, and then you're basically learning individual steps of a gradient descent procedure. So there's a lot of theory behind this. So if you like that kind of stuff, you can find a lot of cool stuff to read about. Anyway, so we want to use gradient boosting for predictions. Let's go ahead and use gradient boosting for predictions, and we can already see gradient boosting doesn't really have any, it has a very expressive prior. I guess that's a good way to put it. It has very high representational power. It can have biases. It can have all sorts of stuff. It's a very powerful method, and you can already see we're not making errors in the thousands anymore. Now our errors are pretty simple, up to the hundreds. The red line is a lot more prominent, and you can see we are a lot closer to the red line. More importantly, you can also see that we are not over predicting over here anymore. We are actually a lot more conservative with our predictions. We are predicting fewer number of games. So this is why our green line doesn't really go up much. It sort of stays at this level. So we have essentially achieved our purpose of, can we have a model which gives us low value so we don't make those big mistakes? Gradient boosting does give us that. And if you look at our error metrics, we can see we have significant improvement on every one of them. It does better than the buy till you die. But once you start getting into this issue of, I want to bias my solution, my learning model a bit, then you start losing out on some of the nice properties that the buy till you die model had. For example, remember the distribution plot we had on the population? The buy till you die was a pink curve. The actual was a red curve, and they're pretty close together. If you look at the gradient boosting distribution, you can see it actually deviates significantly from the actual distribution. The probability for people having a large number of games drops, which is something we wanted. So that's something we wanted. Unfortunately, we lose a lot of stuff in this region, this part over here. There's a lot of overestimation of the number of people who are playing games in this range, 1 to roughly 50, and then the number of people who play 0 games has just dropped down. So it doesn't really capture the actual distribution. It doesn't do a good job of that. It does well when you look at the error rate on the average error rate over the population, but if you look at the distribution, it loses some of those really cool properties that the buy till you die model was capturing. So the next logical step is going to be, can we get the best of both worlds? Can we have the nice property of the buy till you die model, where it was doing a good job of capturing the distribution? And can we also get the nice property of gradient boosting, where we have these relatively low valued predictions? And the answer is, turns out we can. So what do we want to do? We want to look at the buy till you die model's predictions. And then we want to look at the gradient boosting model predictions. And you want to use both of them. So specifically, you want to, how to explain this? You want to remember these values. So it's like, okay, if you're familiar with Bayesian statistics, it's like having a prior, right? You have a prior. So a prior is prior information. That's knowledge you have. And then anything you see, your observations, are the observations that add to any knowledge the prior had, right? And then you have your posterior, which is basically the knowledge you have after the prior is combined with the information of your observations, right? You have a coin, you feel, okay, I think this is a 50-50 coin. You toss it 100 times, it's like 70 and 30. So you say, okay, maybe it's not 50-50, maybe it's, maybe it's like 65-55, or maybe it's 70-30. So you want to, so in machine learning, this is formally called regularization. You want to retain some previous knowledge. You have new evidence. You don't want to lose all of the previous knowledge. So we're here, we don't want to lose the good parts of the buy till you die model, but we also want the nice parts of the gradient boosting model. So what do? We learn a decision tree. We have a third model. This third model is going to learn which parts of my feature space the buy till you die model does well, and which parts of my feature space the gradient boosting model does well. So next time when I get a user and someone says, okay, predict how many games user UI is going to play, the buy till you die model is going to give its buy till you die prediction. The gradient boosting model is going to give its own prediction, or our new regularized scheme where this decision tree model is going to look at this user UI, and then it'll say, okay, based on how this user looks, I think the buy till you die model will do better. Or it'll say, I think the gradient boosting model is going to give a better prediction. So you basically have like a prediction selector or a model selector that's sitting on top of these two models. And if we look at the results for this regularized gradient boosting method, we can see that we actually have improvements across all the three errors. Now, even though the squared error loss doesn't have an appreciable improvement, the mean relative absolute error has a pretty big improvement, and the mean absolute error also has a decently significant improvement. So what does this mean? It means that when it comes to the bigger mistakes, our regularized method does almost as maybe slightly better than the gradient boosted method. But when you come to the lower valued predictions, which is what the mean relative absolute error focuses on, you can see that the regularized version has much better predictions on the lower valued responses. And we can actually see this graphically. So if you recall, this is the distribution that gradient boosting gave us. And when we regularize it, you can see the distribution of the regularized one, which is the bluish colored curve. It's a lot closer now to the buy till you die and the actual curve, versus something like gradient boosting that kind of messes up this portion. Now, this part we do want it to go down because we want our model to have a lower probability for higher number of games. That's the biasing we wanted to introduce. But we retain the performance on this section of the data. So this is how we kind of get best of both worlds in our results. And if you look at the error quantiles, once again, you can kind of see the story from here. The pink curve is the buy till you die model. You can see it does really well for most of the data. But then, again, like we saw, the problem with the buy till you die model is when it makes a mistake, it's a big mistake. So it doesn't make that many mistakes, but when it does, it's a big mistake. So which is why this curve shoots up towards the end. The gradient boosting method, vanilla one, which is the green curve, you can see that, as we mentioned, it uses a squared error loss function. So it focuses more on reducing the bigger errors. So you can see over here, this part has now been brought down. So your bigger errors have come down, but it doesn't really care that much about the smaller errors. So now you're making mistakes on the low value responses, the small errors. So you're making a whole bunch of small errors in this entire range. And then we have the regularized version, which does the best of both worlds. It follows the profile of the buy till you die model for the initial section of the data set of the quantiles, and then later on it starts being closer to the gradient boosted curve, because most likely in those regions of the feature space, there are some regions where gradient boosting does better because the bias it introduces, it's worthwhile, right? Your variance error is happening in this range where there's a large number of games played. So if you introduce a bias of having lower probability, you're going to do better on those points. So that's basically it. So this is you know, you can see the same profile for all the three loss functions. So over here we have, you know, what have we essentially done? We started out with this really cool statistical model with, you know, decades of research and theory behind it that works really well with population level stuff, doesn't do too well with individual level stuff. We picked the state-of-the-art machine learning algorithm that's designed to do very well on individual level predictions. It doesn't really assume anything about the data generating distribution, or it assumes as little as possible, which is why it's not able to do a good job of capturing the population level trends. But we have the buy till you die model to do that. So we saw a way in which we can combine these two things together, and we get the best of both worlds. So then, you know, some of the questions that arise from this: can this be extended to other scenarios? That's something. Again, this is all stuff that we are looking to explore. What is actually happening from machine learning theory perspective? So, you know, we had all these ideas around trading off variance error for bias error and regularization. So maybe a more formal treatment. It would be worthwhile to explore it in a much more formal manner. But really, it's all about taking the idea and seeing how generally applicable it is. What exactly is it doing there? And a brief note. When we look at the largest error after applying everything, when we look at the regularized gradient method and we look at the biggest errors it's making, we notice that some of the largest errors are because of something called the win-back phenomenon. So the win-back situation is when somebody who left the game comes back. So just to give you guys an example, one of the data points that this is making a mistake on is, say, there's a user who played 50 games in 3 days, and then he was gone for 4 months. Nothing. And then he comes back in the test period and he plays 150 games. So there's at the end of the day, you can only predict based on the information that your features have, right? If your features don't have information that can distinguish between different responses, then you can't really predict it. Then it's as good as the process itself having stochasticity in it. So if we want to distinguish further, then we are going to need either like some win-back phenomena model, maybe have more covariates, which would also be another interesting direction to explore. Like, what if we had covariates in the gradient boosting side, and we use a buy till you die style homogeneous parametric model as a prior for covariate based prediction? So that would be another interesting scenario to look at. So some interesting future directions over here. As far as action items, we plan on using this in support of some of our new mobile products. Wargaming has a lot of new mobile games coming out. There's World of Warship Blitz, it's already come out about, I think, end of January. And then there's a lot, I think they have about 7 more games planning to come out. So a lot of these techniques, some of these techniques which we are building for these products. And if you recall, one of the things I talked about, one of our motivations is to use methods that can work with minimal features that don't use personal data. So because, you know, mobile is where you really want to focus on retaining as many users. You don't want to bog them down with personal information questions. One last thing I wanted to mention, once these models are developed, then the next step would be to work with the CRM, the customer relationship management teams, and then every data science product that we develop at Wargaming, it goes through an actual validation cycle. So we have the technical evaluation, the stuff I showed you, are the error rates better on test data, on all sorts of cross-validation errors. You can do all that. But at the end of the day, the final test would be when an actual CRM person uses the predictions, and then maybe they design a campaign around it or something, and then they look at the actual ROI improvement. So that would be the next step for this particular model. There's a lot of validation of this form we do at Wargaming. Unfortunately, I am not at liberty to discuss any details around any of that stuff. But yeah, that's typically the process we follow. So we have our prototyping, there's technical validation, there's a more rigorous validation with CRM where we test actual business use cases, and then you finally have a deployment, you have automation and production when it goes out into production. So that's really all I have. If you guys have any questions, feel free to reach out to me. Any questions around this. I didn't really go too much into the math and theory because I felt that this would be better for a more broader audience. So I didn't really delve too much into machine learning theory. Otherwise, you could spend hours and hours discussing some of these things. People have written multiple theses. So anyway, check out these links. Wargaming, we are always interested in hiring. Some of my colleagues are here, Katrina and Yarushka. Feel free to talk to them if you have any questions. Yeah, if you have any questions for me, go ahead.
Just leave the first link,
Okay.
try it next week.
Okay.
95% finished.
Okay. Go at the second link right now. Go at the first link after a week. So.
Anyone have any questions? Okay, I have a question.
Sure.
What other problems do you solve here? I mean, the problem you introduced is kind of simple one.
Mm-hmm.
So what are the more complicated ones?
More complicated ones. So honestly, like the way it works is like once you start working on a problem, you come across the complications. So we started with a simple model. There was this queue which was causing problems. We added some machinery which fixed it. Now there's this win back problem which I talked about in the very last slide. You would make a modification to fix that. So it's a very iterative process. To be very honest, in my experience, it's very, very unlikely that you're going to sit down, you'll develop a really complex model from scratch and you'll go out there and deploy it. And then it works and everything's good. It really never works that way. You always start out with something that's easy to implement, easy to test, easily scalable. And then that gives you a baseline, right? Even if you do come up with a method, you want to compare it to something, right? You don't want to go up with a situation where you go with this super complex model and then somebody is like, oh, why don't you just count this and divide it by the average and you could get the same thing, right? You want to try the simple basic stuff first, see how that does, and then you want to add in the heavy duty machinery as and when you need it. So. Yes.
Question about a decision tree.
Uh-huh.
What variables does it usually use to decide whether it chooses this model or this one? How does that work?
So, okay, I'll repeat the question. The question asked was, how does a decision tree decide?
Yeah, what variables are typically used? If there are any typically.
Decision. So, is this a general question about decision trees? Where are they used? How are they used?
No. It's actually about this decision tree.
Okay, this decision tree. So, right, I didn't really go into the details. Let me just quickly go over this. So, remember we had our training data from 1st Feb to 31st Jan. We further divide this into 2 more parts. And we use that division for training our decision tree model. So, it's like your training. So, let's say your training data is 200 days. You're predicting on 90 days. The 200 is divided into 110 and 90. So, that's it.
Did you try to ensemble more than 2 models?
I did try. I tried random forests. I tried other, Generally, honestly, typically random forest gradient boosting are the best. You can try bagging in other stuff, but in literally 90% of the learning problems right now, random forest, gradient boosting, deep networks, one of them is probably going to do better than everything else. So gradient boosting was the best one out of all the other ensemble methods. So that's it. All right. Anybody else? Oh.
Could you tell us about some other machine learning or data science products you are using?
So other machine learning data science products. So the most popular ones right now, I would suggest you have so H2O is pretty good. Spark is really good. Spark is more for having very large data sets if you have huge data sets. H2O is also generally a lot of machine learning technology is moving towards being able to run on very large data sets, because honestly a lot of it is also moving towards deep networks, which is designed to work on very large data sets. So you have the Python, you have libraries in Python, you have R, H2O, Spark. I would say these are SAS if you can afford it, really. So, which we can because we are a big company, but but yes, that's the other good one. There's the sorry again.
About like use cases.
Mm-hmm.
I mean, data products as the product you presented here.
You mean like how is this implemented in the final?
No, this is to predict churn.
Mm-hmm.
So what other
Predictions?
use cases are
Oh, okay. Other use cases. So, actually, honestly, like it covers a very broad area, like BI in general. So right now we looked at a small portion over here. So this is essentially a kind of like a CRM support LTV. So this would come under publishing support. But other problems like, is a player cheating or not cheating? It's a prediction problem, right? Look at the activity of a player and predict. Is he using a cheating program or is he not using a cheating program? Skill estimation. We have so many people playing games. Can we rank them in order of skill? There's some more statistical stuff like survey design. So there's a lot of stuff all over the place. Once you have an organization this big with so many different divisions, you're bound to have data science challenges, especially with a data set this huge. Like I said, hundreds of millions of users over so many games over many years, and it's data that's very fine. Individual tank shells fired. So there's a lot of stuff to look at. You can manufacture your own prediction problems if you have data like that.
What was the most significant feature?
The most significant feature, I would say recency was the most important indicator because, and that's honestly really what was also throwing off the buy till you die model. So it's a very strong indicator of someone's going to come back and play anything or not come back. So it always started out with that. So anybody? Okay, thank you everyone.